I just want to point out again, I hope I'm making it clear. So this is the peroxy hydroperoxide alkyl radical that would be formed for n-Heptane. And then this isomerizes, generating what is referred to here as a P.OOH2 radical. So it's a radical with two hydroxy groups on it. We don't normally, in the mechanisms, we don't write this radical because this OO bond will cleave very easily at a very high, fast rate, producing the keto hydroperoxide plus OH directly. So normally in the mechanism, if we include a step producing this radical and then this radical decomposing to the keto hydroperoxide plus OH, or just having the isomerization going directly to the keto hydroperoxide plus OH, we say the same reactivity, okay? But strictly speaking, if you want to be technically correct, you should write it as two steps, okay? However, by writing it as 2 steps, you then have to include all of these species in the mechanism and adds more complexity to the mechanism. And hence, when we published the mechanism originally, we didn't include these species. We just had it go directly to the keto hydroperoxide plus OH. I want to point that out. However, now we want to add these species in, these P.OOH2 radicals, because we want now for all of these species to have alternative reactions available to them, okay? Whatever they may be, okay? So, for instance, if this radical generates a cyclic ether, so instead of decomposing to the keto hydroperoxide, but we include a rate in which, remember now, if we had this species can lead to the generation of a cyclic ether plus OH. So we allow this species too. Even though it is an OOH, it gives an OOH cyclic ether species plus OH, similar to this one, okay? And if we include those in the mechanism, it does increase the reactivity slightly. So some of them do occur, but it doesn't have a huge effect on the prediction of the mechanism. But we include them, they're allowed to happen in the mechanism, and they should happen at similar rates to the formation of cyclic ethers in the case of the hydroperoxy alkyl radicals, okay? So we're adding that, allowing that to happen, okay? If we also allow these reactions now, the alternative reactions are a direct concerted elimination of a hydroperoxy alkyl radical, similar to an RO2 giving olefin plus HO2. Actually, we don't see that this is competitive anymore, and it doesn't seem to change the reactivity at all. But we include them in the mechanism, but it makes no change to the predictions, okay? But we're allowing the mechanism to allow them to happen in the mechanism, okay? Okay, so this is just showing you then the effect of the alternative pathways, okay? So okay, so this is just showing you, okay, here's our experimental data. Here's the prediction of the Healy mechanism, okay, as it was, using the old rate rules for n-Heptane and iso-Octane that we published previously. And then if we add these alternative isomerizations, these are the ones now, remember, that lead to the formation of an olefin plus HO2. So instead of just allowing isomerization of the peroxy hydroperoxide alkyl radical, abstracting only the hydrogen atom which is bonded to the carbon, which is bonded to the OH group, we allow all the alternatives. So we allow isomerization of the 5-membered rings, the 6 primary, the 7 secondary, and the 8 primary. We allow all of those to happen. If we include all of those in the mechanism, and then the subsequent decomposition of those species, we see a lower reactivity at low temperature, and a higher reactivity at high temperature. And then remember, that's due to the generation of the olefinic hydroperoxide plus HO2. So we're getting HO2 formed. So HO2 is less reactive than OH at low temperature and more leads to more reactivity at high temperature because we're getting 2 OH radicals produced. Okay? But in the current mechanism, by including these alternative isomerizations, it does slow things a little bit at low temperature and increase things a little bit at high temperature, but it's not nearly as influential as it was, because now we have the new thermochemistry and we have the new kinetic parameters included in the mechanism. Okay? So they do influence things a little bit, but not nearly as much. Okay? And then as well, if we take this radical and we allow it to form a cyclic ether plus OH, in the old mechanism, it made a huge difference to the prediction of the mechanism. Now, it makes a little bit. It does increase reactivity, but again, it's not nearly as pronounced as it was previously. They are included. They make a difference, okay? But it's not nearly as pronounced as it was, okay? So, okay, so if we look then at the predictions of the mechanism, sorry, these are experimental results now, here, these symbols, obviously. And then these solid lines are constant volume simulations of the data using different reaction rates for peroxy, hydroperoxy, alkyl radical isomerizations to the carbonyl hydroperoxide plus OH. And you can see using rate constants calculated by Sharma, working in Bill Green's group at MIT, or Professor Miyoshi in Japan, or Stephanie Villano and Tony Dean at Colorado School of Mines. For n-Pentane, the use of all 3 different rate constants, they're similar. They are different, but they're similar, and you can see that we get similar results. And then if we include facility effects in the experiments, you can see that the predictions are actually quite good. They match the data. This is including heat losses and so on in the calculation. Okay. For iso-octane, though, the predictions aren't as good. Okay? So if we use Sharma, Miyoshi, and Villano and Dean's rate constants, and what we're doing in these cases is, if we take their rate constants for isomerization for RO2 to QOH and apply them to the O2 QOH, the second isomerization step, and what we're doing is we're lowering the activation energy for abstraction of the hydrogen atom bonded to the carbon, which is bonded to the OOH by 3 kilocalories per mole, and we're basing them on the RO2 to QOH isomerizations, then it works pretty well for the case of n-Pentane, but not very well at all in the case of the branch 2-methylbutane, iso-pentane. Okay? So, and here's the prediction using for constant volume, and here's the prediction including facility effects. And you can see, even including in facility effects, the mechanism's too fast. So that doesn't work in those cases. Okay. However, and the reason we did that is because Villano and Dean, as I said, didn't study the second isomerization step. They didn't provide rate constants for this isomerization. So we had to use the rule of thumb that we were using, or the rule that we used before. Okay? However, Sharma and Bill Green's group did. They looked at both RO2 to QOH and then O2 to QOH to the carbonyl hydroperoxide plus OH. So they looked at both of these steps and provided rate constants for both. Okay? So instead of doing this crude way of lowering the activation energy for the first one, for the second one by 3 kilocalories per mole, if we use the rate constants that are actually calculated by Sharma and Green and by Miyoshi, this is what you see in the mechanism. So you see good agreement, again, for n-Pentane, right? Particularly when you include the facility effect, okay? But you see also good agreement if you use the Bill Green's MIT rate constants calculations, okay? When you include the facility effect. But when you use Miyoshi's, it's not as good. Okay? So this black line is when you use Bill Green's without including facility effects. When you include facility effects, now the agreement is pretty good with the data. Okay? But Miyoshi's are too fast. Okay. So what we were doing before isn't good. And what we now do is we use the rate constants calculated by Bill Green's group for the second isomerization step, because we're getting better agreement. It doesn't matter what you use for straight N-alkanes, straight-chained alkanes, but it seems to matter for the branched ones. Okay? And that's what these slides are showing you. Okay. And so we recommended we lowered the activation energy by 3 kilocalories per mole, as I said. But actually, if you use the Sharma ones and you look at the activation energy barriers, they're actually 3.3 kilocalories per mole lower for 5-membered rings. So that was a reasonable rule of thumb for 5-membered rings. But actually, for 6-membered rings, they're only 1.7 kilocalories per mole lower, not 3. Right? And they're only 0.4 kilocalories per mole lower for 7-membered rings. Relative, I'm talking now relative to RO2 to QOH isomerizations. Okay? And so if you look at this, what did I say? What ring transition state rings size, leads to chain branching, typically? 6-membered rings. 5-membered rings lead to less cyclic, or olefin plus HO2. 7-membered rings lead to cyclic ethers. 6-membered rings go on to chain branching. Okay? And what you're seeing here is that this favors the formation then of 5-membered rings. And 6-membered rings are less favorable relative to what we were doing before. And if that's the case, then these Sharma rate constants will make the reactivity of the system lower. And that's what we see. Okay? So that's why I have these arrows here. This increases the rate constant, the reactivity of the formation of 5-membered rings, and lowers the formation of 6- and 7-membered rings. Even though the isomerizations through 6-membered transition state rings still dominate. Okay? They still do dominate, but they're not as important as they were relatively. Okay? And so if we then apply those rules to all of the pentane isomers, so we have N-pentane, and this is just looking at isomeric structure, isopentane, and neopentane. So let's look at N-pentane and isopentane. Okay? We see that N-pentane is much faster in the low temperature regime than isopentane. Right? And that makes sense because we have the straight chain structure, and we can have more 6-membered primary and secondary transition state rings leading to chain branching. Okay? For the isopentane, we have fewer 6-membered transition state rings. And also, we have more primary hydrogen atoms involved in the ring. And that primary hydrogen atom is going to increase the activation energy in the isomerization and lead to lower reactivity. And so, hence, okay, they parallel one another, and isopentane is considerably slower than N-pentane. And then in the high temperature regime, both of those isomers have about the same reactivity. But neopentane is very different. Okay? Neopentane is actually more reactive here in the NTC region than isopentane. Because neopentane doesn't have a 5-membered transition state ring, which can lead to an olefin plus HO2. So if I can draw that. Okay, so we generate the radical, we add molecular oxygen, and then we isomerize. Okay, but this cannot give us an olefinic species plus HO2. There's no beta. This bond is alpha, this bond is beta. beta scission is going to lead to the formation of iso-Butane plus formaldehyde plus OH. Okay? So this is going to give you C double bond C plus formaldehyde plus OH. Okay? But we cannot, from the hydroperoxy alkyl or neopentyl radical, we cannot get olefin plus HO2. And this generation of olefin plus HO2 in alkanes leads to strong negative temperature coefficient behavior. So you see in neopentane, we don't have nearly as strong negative temperature coefficient behavior as we do for N-pentane or isopentane, 2-methylbutane. Okay? Not only that, but the reactivity of neopentane out here at 900, 1,000, 1,100 Kelvin is much lower for neopentane than it is for N-pentane and neopentane. Why is that? Because we get the formation of iso-Butane, which, if we abstract a hydrogen atom, leads to the formation of an allylic radical, methylallyl radical. A methylallyl radical is resonantly stabilized, and it's hard to oxidize it. It consumes HO2 radicals. Okay? So it'll consume a HO2 radical, generating an alkoxy radical plus OH. Okay? If HO2 radical was able to react with something else, it would give you H2O2, which would give you 2 OH radicals, not 1. Okay? And that then leads to the decreased reactivity of neopentane out here in this region, because HO2 is the important radical at that condition. Okay? In addition to that, a little bit is due to the fact that some R plus O2 is still occurring for N-pentane and neopentane given RO2. And then they can go on and generate olefin plus HO2. I remember I said that's part of the reason, a little bit of a contributor at least, to the reactivity. Rich mixtures are faster in this region because of that reaction. Okay? Neopentane can't undergo that reaction. And hence, for all of these reasons, neopentane is considerably slower in this regime compared to N-pentane and 2-methylbutane. And you can see, actually, the reactivity of N-pentane and 2-methylbutane are almost identical throughout this range. And then the difference in reactivity in this regime is due almost entirely to the lower reactivity of the resonantly stabilized radical produced from iso-Butane, because it's the main radical produced from neopentane. Okay? So I think this is a very nice slide showing the different reactivities of the different fuels due to the different chemistry associated with their oxidation. Okay, so this is just showing you then the success of looking again at the new rate rules, providing or understanding. I should go back. So based on what we've done now, by including all these reaction and alternative reaction pathways, I hope you can see, okay, the alternative reaction pathways do play a small role in the oxidation process. But our overall understanding of the general reaction pathways for low temperature chemistry were correct. But we had the wrong thermochemistry, and because we had bad thermochemistry, we used bad rate constants. Okay? So, but the recent calculations using what I think is better thermochemistry leads to better understanding and better agreement of the models and a more high fidelity understanding of what's going on. One thing I think for the future going on is we need to have then very high level thermochemical, high fidelity thermochemical data for these low temperature species. If we do, then we should be able to get good models for these species. Not only for alkanes and branched alkanes, but for alcohols, ethers, esters, and so on also. Okay, so this is just showing you then how we'd say the old mechanism based on the rules for n-Heptane and iso-Octane that we published previously, and the new model performs. And you can see the solid line is the modern model, the dashed line is the performance of the previous model, and the solid line captures the data much better. This is showing you that was for n-Pentane. This is showing some data for n-Butane. Again, the solid line are the more modern rate constants. So these are using now the modern rate constants, applying those rate rules to C4 species, not C5, but C4. And this is something similar. This is validation of, this is looking at the concentration of the ketohydroperoxide formed in a reactor. This is from Craig Tages, and this is from the synchrotron photonization measurements of reaction of iso-Butane in their experiment, which is published in 2013. And you can see this is the old model predictions of the ketohydroperoxide formation for 3 different concentrations of oxygen reacting with iso-Butane. And you can see this is the modern prediction of the mechanism now. So it's capturing the concentration effect of O2 reacting with iso-Butane at low temperatures. Okay? This is then validation, further validation for n-Pentane. This is looking at validation for n-Hexane, the same thing. And then these are speciation validations against jet-spurred reactor experiments. And you can see the value of getting all these species at low temperatures, particularly these cyclic ether species, these C6 olefinic species. They help test, are we getting the RO2 to giving you olefin plus HO2 rate constant correct? Are we getting the formation of the cyclic ether correct from the hydroperoxy alkyl radical? So these species measurements in particular are very valuable at low temperatures. Okay, and then the same thing has been applied to n-Heptane, and we have good agreement with n-Heptane too. Okay, so this is really the paper then. So where I synopsize, and if you want to read a better synopsis maybe than what I've given here in the lectures this morning, this paper was published last year, I think, in JPhys Chem, which tells the story that I've just told you this morning. Okay, I should have the exact citation, but you should be able to find it. Okay, we also published earlier this year a validation paper then in collaboration with Eric Peterson's group in Texas A&M University, where we show the prediction of the mechanism against experimental data. So that's just that. We've also then, working similarly, is Dr. Liming Chai and Professor Heinz Pitch at Aachen University have been, and working also in collaboration with Mani Sarathia at King Abdul University of Science Technology, where Liming developed rate rules for larger alkanes. So he used, not by hand, or like I've been showing you, but he used a computer to optimize rate rules for n-alkanes, for going from, I think, hexane up to n-decane. Okay? And then what he did was, he said, right, let's get some optimized parameters to, and it was just for ignition delay times. So let's get optimized parameters just for ignition delay times for all of these fuels, and came up with, for all the reaction classes that I've just been talking about, came up with optimized rate rules for those. And then he said, right, well now let's develop a mechanism then for endodecane and see how ab initio it compares against endodecane data. And it actually did very well. Okay? So what we hope to do is now go a step further together, working with him, and apply this procedure to also branched alkanes, so that we can have some sort of a rate rules for all alkanes, if we can. Okay? That's the next step. And then if we can get it to work for alkanes, we'll try and apply it to alcohols, and then ethers, and so on. okay? So step by step, and build up our knowledge for all of these. And then we should be able to get very high fidelity mechanisms for lots of different fuels at low temperatures. All right? So this paper has just been accepted to Combustion and Flame, and it will be available very soon. I don't think it is yet, but it will be available very soon as a paper in press online. Okay? So just watch out for that. Okay. I don't really want to go into this. We have data on the hexane isomers. It's just branched species. And then we have data also on that's the hexane, and we have heptane isomers. And again, you can see we took data in a rapid compression machine. You can see that the reactivity, so here we have inverse temperature, here we have ignition delay time, and heptane is very reactive. We weren't even able to measure it in the rapid compression machine. It's so reactive. But the 2-methylhexane, which is an octane number of 65, shows much lower reactivity. And then the one with the lowest reactivity, 2,2,3-trimethylbutane, which is a research octane number of 112, showed the least amount of reactivity. And so what we're going to do is, as I said, work with Professor Pitch's group at Aachen to use these data in hexane and isobutane, heptane isomers and heptane isomers, to develop rate rules for the branched alkanes too. And hopefully we should have a consistent set for both straight-chained and branched-chained alkanes. Okay. I won't go through this. So, well, I will. Okay. So we reevaluate our understanding we've reevaluated our understanding of low-temperature oxidation of alkanes recently. We've developed rate rules for reaction classes important in the low-temperature regime. The alternative pathways have little effect on our simulation results now. Okay, they have some, but little. And from the source of the long-standing discrepancy between mechanisms of straight and branched-chain alkanes stems from the thermochemistry. Okay, so really, the thermochemistry is very important to kinetics. Okay, and you can see it clearly here in this process that it was ultimately it led to us understanding the low temperature chemistry. Okay, so we want to revisit the primary reference fuels and so on going forward. Okay, so now, has anyone any questions, or is that enough on that? Okay, we'll move on to some interesting features of biofuel combustion. So here, again, the kinetics are similar, but there are certain reaction types that occur that don't really happen or aren't as important for alkanes. So let's look. So why are we looking at biofuels in the first place? Okay, because we're looking for new sources of energy, and there will be all sorts of different sources. And I think it's not going to be, one source or another. It's not going to be exclusive. It's going to be mutual. So we're going to have to use all different types. So wind, solar, geothermal, and so on. But combustion will still be a big contributor. Okay, and so actually, combustion is responsible for most of the power generation in the world. It's responsible for 85% of EU power production, right? 90% of transportation power. And we have perhaps about 100 years of fossil fuel remaining. And alternative energy sources aren't very mature. You would estimate 50 to 100 years needed for their development, okay? And we also have a huge infrastructure, so all the gas stations and so on around, all that is there now, okay? And how do we replace that? That's a huge, huge cost to the economy in terms of replacing the infrastructure. So the challenge for us as combustion chemists is to limit the adverse impacts of fossil fuels and buy time for the generation of alternative energy sources from wind and wave and so on. Okay, so in the future also, some petroleum will still be available, but we'll also be getting hydrocarbon fuels from oil sands and oil shale in Canada. We'll be getting it from coal to liquid processes and Fischer-Tropsch processes. We'll be using natural gas and gas from fracking, and also hydrogen generation from catalysis, or electrolysis, I should say. And bio-derived fuels, such as ethanol, butanol, and algae, and biodiesel from vegetable oil and animal fats. Okay? So these will all be sources. But we need to understand then the kinetics of all these different types of fuels so that we can use them in combustors. Okay? And this is just showing you, for instance, if we have different Fischer-Tropsch fuels. Okay? So here's centronium, and this is just showing you a carbon number here. So here we have centronium, which is about 22% N-paraffin and mostly isoparaffins. But if you get to something like Sasol oryx, it's about 72% N-paraffin, and the rest is isoparaffin. So they're going to react differently because we have here a lot of straight-chained alkanes. Here we have a lot of branch-chained alkanes. And as you've seen, the reactivities can be different. Okay, I won't bother with that slide. Okay, so this is just showing you then, it's a slide taken from a paper that Charlie included me as co-author or co-wrote with him in 2006. But it's based on an idea from Miyamoto in an SAE paper in 1998. And it shows you the percentage of fuel carbon converted to sub-precursors on the y-axis versus the fraction of oxygen in the fuel by mass. Okay? And so here, if we just follow dimethoxymethane, for instance, DMM is dimethoxymethane. MB is methylbutanoate. TPGME is tripropyl glycol methyl ether. Ethanol, methanol, dimethyl ether, and dibutyl malleate. Okay? See, these are all the fuels. So if we follow dimethoxymethane, we have, okay, so there'll be 0% of fuel carbon converted to sub-precursor when you have 100% dimethoxymethane in the fuel. Because, and a good rule of thumb is, if you have no CC bonds in a molecule or in a fuel, then you won't get soot. Okay? And you can see here that you can get a large reduction when you get a lot of DME present. Again, because there's no CC bonds in the fuel. You've got COC bond in the fuel. Okay? So including oxygenated species in the fuel will decrease the sooting tendency. But of course, your energy density is going to decrease because you're replacing a carbon and two hydrogens, or carbon and hydrogen, with oxygen atom. And so you won't be getting the energy out of that. Okay. Anyway, so if we want to have cleaner burning fuels, which have oxygen in them, we need to understand how fuels with oxygen atoms, the kinetics of their combustion. Okay, so if we consider alcohols such as methanol, ethanol, propanol, butanol, for instance, we've also looked at esters, ketones, and furans. And I'll talk about all of these different types of fuels in the coming slides. Okay, so let's look at alcohols. And as I mentioned in an earlier presentation, we spoke about alkyl radical decomposition and how we estimate those, and how vinyl alcohol was formed from one propanol and not two propanol. So we had a study on propanol isomers in 2009 that we published. And here are ignition delay times measured for N-propanol and isopropanol. And you can see clearly here, we have the same amount of fuel and oxygen at equivalence ratio of 1 and 1 atmosphere. And again, we increase the temperature, go from low temperature to high temperature, the reactivity of the fuels increases. And you also see that N-propanol is always faster to ignite than isopropanol. I don't know, is it about a factor of 2? About that, maybe a bit less than a factor of 2, okay? But it's about that magnitude, okay, throughout the range, okay? So why is N-propanol faster than isopropanol? Okay, and if we do, as I was talking about before, actually this is a bit more than I was saying, maybe 10 or 20%. This is performed at 30% fuel consumed. Okay? So we look at the edit of the output from the computer simulation, and we follow the chemistry at this particular condition. So we have 5.5% N-propanol at 5 sig to 1 and 1600 Kelvin. And we have 30% fuel consumed in both cases. I think there's 29 in one and 30 in the other. So, but it's 30%. And you can see for N-propanol, it's undergoing this unimolecular elimination reaction, producing propene and water, and 30% of the fuel is of the fuel that's consumed. So this is 29% of 30%, if you want to put it that way. Okay? So I'm normalizing that 30% to 100%, if you follow what I'm saying. Okay? And if we then normalize also isopropanol, in the case of isopropanol, at the same amount of fuel consumed, 63% of the 30% that's consumed is going to propene and water. So concerted elimination reaction is more important for isopropanol relative to N-propanol. We're getting twice as much propene and water for isopropanol relative to that of N-propanol. And because of that, isopropanol is twice as long, takes twice as long to ignite, or N-propanol is twice as fast as isopropanol. And it's due to this molecular elimination reaction occurring at this condition. Okay? And why is that? So if you look at the sensitivity analysis, then, to ignition delay time, you see that the most inhibiting reaction is the production of propene plus water. Okay? And one of the most enhancing reactions is one producing methyl plus this C2H4OH radical. Okay, so this is SC2H4OH. And you can see that this is going to give us acetaldehyde plus H. So if we get bond cleavage, if we look at the molecule again, so if we get the CC bond cleavage, we get this radical plus methyl. And then that will give us acetaldehyde plus H. Okay? And that, by giving us H atoms, we get more reactivity. Okay? But if that is competing, or if this reaction, the concerted elimination reaction giving us, or sorry, the elimination reaction giving us propene and water competes with this, then we won't get the H atom, and we won't get the branching. Okay? So hence, the more of this we get, the less reactive. That's one reason. Can you come up with another reason why this would lead to reduced reactivity? There's a double bond in propene. Okay, so you said because there's a CC double bond. And what's the double bond in propene going to do? Not the more energy to break that bond. It is because of that, but that isn't the main reason. Okay, because when it gets oxidized, it's going to, so you said correctly, when it gets oxidized, it's going to form the allyl radical. And that's not going to be reactive then. It's going to be difficult. And if allyl radicals are formed, what are they going to do? They'll react with HO2 radicals, giving us allyloxy plus OH. So we get one OH radical. If HO2 was free to react with other species, it would form H2O2, which would give us two reactive OH radicals. Okay? So hence, these resonantly stabilized radicals inhibit reactivity or reduce reactivity of the system. Okay? So not only do we not get the H atom formed here in this competing reaction, but we get propene, which will oxidize to give us allyl radical, and then that's going to inhibit reactivity because it's a resonantly stabilized radical. Okay. Again, you see the same thing in N-propanol. We have this reaction inhibiting reactivity, and then this reaction promotes reactivity because both of these radicals, ethyl and hydroxymethylene radical, are both going to give you H atom. Okay? And they promote. Okay, so where do we then get the rate constants for the elimination reaction giving you propene plus water in both cases? And these are the rate constants we use, and it's taken from a paper, an older paper by Wing Zhang in 1976. So believe it or not, there was kinetics done back in the 70s, okay? And Wing Zhang was a very good kineticist. I use a lot of his rate constant expressions still, and recommendations and calculations. And so this is what he recommended in these cases. And these rate constants are based on his recommendations. Okay? And you can see actually the activation energy formed. So to form it, I've drawn the structure here in a way, maybe it's badly drawn, but it's in a way to show you that you have a four-membered ring here in the transition state where the hydrogen can migrate to the oxygen atom, and then you get the formation of propene and water. Okay? And it's easy to see that. Okay? However, in the case of N-propanol, you have one methyl group here with this hydrogen. But in the case of isopropanol, you have two. So isopropanol should be at least, based on degeneracy, at least a factor of 2 faster. And actually here, we're using a rate constant that's about maybe, I don't know, more than a factor of, close to a factor of 7, is it? At least a factor of 6 faster, okay? So anyway, you can see clearly, just based on degeneracy, there's 2 methyl groups here, that there will be more H atoms available to undergo this molecular elimination reaction. So even though we use the same activation energy, the frequency factor here is higher, okay? And because it is, then we have the rate of abstraction, or sorry, molecular elimination from isopropanol is about twice that of N-propanol. Okay. This actually was a rate constant that we derived from, or we used in the mechanism for isopropanol oxidation in 2009. And then it's been published now, actually, it was published last year, the year before, where this rate constant was measured here at Princeton in the flow reactor here. And these are the measurements, these 2 black squares are the measurements that were performed here at Princeton for that reaction. So for isopropanol giving propene plus HO2. And you can see that the Johnson rate constant agrees quite well with that measured here at Princeton. Okay? This was a rate constant in the literature for that, which was calculated by Bui et al. I don't know exactly, I can't remember. I think it was MC Linz. Okay, so that's the reactivity of alcohols. So let's take a break now, and we'll come back and we'll do the reactivity of ethers and other species as well. Okay?